And let me start from the beginning. We had a model, right, that had a reservoir here and a tank over here, and everything was built, and we were told that a new commercial site was going to be built here at J500, so we had to, for sure, include these new pipes. So we have to size these pipes basically for the demands that have been placed at this node. And actually what we're going to place here is that we're going to assume a fire flow demand of 3,000 gallons per minute. So in the average day, there's no demand there. But all the rest of our nodes that already exist, they have demands. And we're going to run it in a bit and see the results of this system as it is today. So in addition to sizing these two pipes, we had to figure out where it was most convenient to connect, whether through pipes 600 and 601 to connect to this node, or go down here, pipe 800, 804, 803, 802, 801, and 800. Notice that this is a much longer path to connect. Or we had a third choice, which was to go using this 702 nomenclature, so 700, 701, and 702, right? So we were asking Darwin Designer to help us figure out which would make most sense to go the 800, the 600, or the 700 route. Okay, so before we go into Darwin Designer, let's just take a look at the system that we had. Because we are asking, the best solution that meets a certain criteria. So for average demands, notice that the total demands amount to 1,180 gallons per minute. Okay, so that's including every node. J500 does not have a demand in this particular average demand scenario. So let's take a look at our junctions, because I want you to be aware of the pressures. And I'm just going to reset the filter. Sometimes this happens if you have filtered your results somehow. So for average day demands, our pressure goes from 40 psi up to 116. Now, why am I showing you this? Because the pressures are pretty good for average days, but we're not going to design our system for average days, right? We're going to design it for maximum day demands, right? Because for average day, we were going to design it for max day demands, and we had to make sure that every node was able to meet a minimum 20 psi. So obviously, even if I put that 3,000, we're pretty good in pressure right here. So what we did is we went to Darwin Designer and we made a couple of changes. We said, okay, I want you to do a design for least cost. And what does that mean? That you have to figure out the least cost solution that meets the following criteria. That when I have a fire flow of 3,000 gallons per minute at J500, also when my demands, that remember we had said, I didn't write it down, but I think it was 1,180 or was it 1,800? Let me just go back here and review. 1,180. So these are our average. So now we're multiplying all those demands times 1.5. Okay. And if you want to pull out your calculator and do that math, that'd be great. So we're increasing the demands at all nodes. In addition to that, we're adding the 3,000 demand to J500, and we're saying while you're doing that, you have to make sure that every single node meets a minimum pressure of 20 psi. Okay, we also set a maximum of 200 psi. And remember, this maximum, it's basically when it's taking into account the trade-off option that we're saying, okay, try to improve the pressure at a particular node. That's the pressure benefit we were talking about. But, don't ever go beyond 200. And we could even be more um, realistic and say maybe not more than 150 or, even lower because it's never really going to get to that point. Okay, so those are the modifications that we make. And then we said that we're going to group our pipes, right? So the internal are those 500 mandatory pipes that we need to have. And the west, north, and south, south is the 800 route, north is the 700 route, and west is the 600 route, right? So we added those pipes there. We're not doing rehabilitation studies. And we input cost for the 500 mandatory pipes. We name those cost new because we have to have them. There's no option of not putting one of those pipes. And the optional pipes is the cost that we'll be assigning to the 600, 700, and 800 routes, which notice includes a 0-inch diameter, which makes it be optional, right? So we're not telling it to size all the 600 routes, all the 700, and all the 800. Most likely what we're going to see in our results is that it chooses one of those paths, or maybe if it really feels that we're doing a trade-off and we want to improve the pressure by quite a lot, it will do 2 runs, right? Obviously at a greater cost. But that's what this 0 diameter means. Okay, and then we did the objective type. For the first run, we did minimize cost. So give me the cheapest solution that meets my pressure criteria while having max day demands and the 3000 flow at J500, right? In the second run, we're going to do a multi-objective trade-off. So we say, okay, I have $500,000. What can I do with that? And remember, the other option that we have is to set the benefit type to unitized or dimensionless. So I'll show you here. When we choose unitized, the benefit is given as the average pressure above those 20 psi, right? So it's simply the P goal is 20 psi, and this is the pressure above that at every one of the nodes. When we do dimensionless, we're doing the same difference, but then we're dividing it by 20 psi so that we're making it dimensionless. The result is not pressure anymore, it's just dimensionless. And it's also weighted by the demand at the node. Okay, so demand at the node divided by total demand. That's the only difference of choosing one or the other. In this exercise, we're going to use unitized. Okay, so let's go take a look at our solutions. I have run already some solutions. So let's take a look at the trade-off solution now that I have already run. In the trade-off is this, basically multi-objective, 500,000 unitized, okay? And I run it and it gives me these results. It tells me the benefit and the total cost of each of those solutions. I feel like we should run this one too, so hold on one second. Let's just run both so that we can get results for both. Minimize cost, and we'll go over here and select only the fire at J500 event. Make sure everything is okay. We'll keep 10 solutions as well, and let's just run this one for now. Okay, so that I want to be able to compare both solutions in one file. Okay, so let's start there with the solutions. The least cost solution is $194,000. Okay, and let's take a look at what that design is. I'm going to do a graph here. So you can see that there's basically no additional benefit. So it's going just for the bare 20 psi at all nodes. Obviously, some nodes will have more than that, but the most critical ones would have 20 psi, which is what we're requesting. And the results here, you can see if I go to my simulated pressure, the worst node is J360, and the required minimum pressure was 20. It can do up to 21.83. So all our nodes meet that requirement. We didn't have anything for flow, so that was the only constraint that we were setting, right? And what is that solution exactly? Well, it's saying 500 and 501 should be 10-inch diameter. Those are our internal pipes, and it gives us the cost to lay each of those. And it says you should connect through the north through pipes 700, 701, and 702, and use 8-inch diameter for those. So with this configuration, we can get the minimum pressure requirements. Okay, so let's go ahead and export this solution. I'm going to call it minimum cost, just because I already have one. Okay. And let's evaluate the other options before we go. Notice that it found options that are a little bit more pricey, like this one, 206, 220. So they're all a little bit pricier, but we're not taking into account the benefit here. So it could be the same pressure. So let's take a look at solution 2, for example. It's saying, hold on, what was solution 1? Okay, solution 1 had the internal pipes at 10-inch and the 700 run at 8-inch. Solution 2 has the opposite. So let's see this solution, what the simulated results would be there. Sort ascending. So the benefit doesn't seem that significant, but it is pricier. So as we mentioned the other day, we have a cloud, if we mentioned it yesterday, of different possible solutions, right? So you could, start evaluating this because they're still perhaps within your budget. So you can see what the tendency of all those possible solutions is. If we take a look at the trade-off, we can see now other solutions that not only are considering the cost, but also the benefit. So let's take a quick look at the options in the trade-off. Here we can see, okay, as the cost increases, the benefit generally increases. Remember, this is kind of that Pareto front, so the most non-inferior solutions. So if we have the 500,000, we could go up to here and have all that benefit. Or we could stick, like we can see there's a big jump here, right? So for a little bit more cost, the benefit really increases, and that seems to be solution number 6, right? So let's take a look at solution 1 and solution 6 here. Solution 1 says internal diameters 8 and the other diameter is 10. Now, what does that do? Let's think about that for a moment. The internal ones are 8-inch, but the external ones are 10-inch. So the nodes in the north area of our model, so the nodes right here, are all going to have better pressure because now there are more pipes and bigger, right? So in terms of pressure benefits, that's a really good solution. Now let's step on solution 6 and see what it is. Okay, it says, the internal ones would be 12 and the north would be 10-inch diameter. So remember, we were trying to improve the pressure, particularly at node J500. So remember when we were here, we went to the design event. Let me go back here to our design events. And we were saying, we don't want to consider the pressure benefit for every node, really only for J500. So let's go see what the pressure at J500 is like, right? So I'm going to go to the simulated result, and I'm going to sort this ascending. That sorting sometimes doesn't work. So let me do, the best way really is to export this out to the scenario and see that. So let's export those two solutions and then we can compare them outside. It's easier. I'm going to export this. I'm going to say trade-off. Yeah, I'm going to leave that same name, Fire 1. And I'm also going to export solution 6. Let's name it 6 so we know exactly what it is that we're talking about. Okay, so now you see all the scenarios here. I'm going to run this one. And you get to see that this particular one, and remember, this is using the, let me go back here and explain this with the graph. When we export the solution, we're exporting the physical alternative. I didn't export the physical alternative. So hold on. Yeah, we have to export these two. Sorry, my bad. I thought I had exported those. So let me re-export those. Okay, so this is going to be this. I had already saved this name, so I'm going to just give it another name. And I'm going to eliminate those other scenarios so you guys are not confused, or at least I'm not confused. Okay. All right. So did you guys see what my mistake had been there? I was exporting this scenario, but I wasn't exporting the changes in physical properties, so the pipe diameter. So it's really as if I weren't doing much. So we're going to keep these three. So let's start with the minimum cost. So notice this minimum cost is going through the 500, 7, 7, and 7, but it no longer has those pipes that were going to the west or the south, right? The 600 or the 800. And let's run it. And we can see the pressures. So let's take a look at the pressure here. 76 psi, because it's not taking into account, I didn't export demands, right? So it's not considering the demand here of 3,000. Now let's see what happens when we add that demand of 3,000. And our demands that are being used in the run are still our average demand. So I should probably add all the demands or increase all the demands by 1.5. But here we can see the pressure to be 30.43. Let's probably do this the right way. I think this was part of the exercise. Let's modify the demands, multiply them by 1.5, except for J500. So I'm going to multiply them all. And let's find J500 because that one cannot be. This one has to be back to 3,000. Okay. All right, so now we can run it. Okay, so you can see here, for example, pump 1 exceeds the maximum operating point for the pump curve. So all those little things you gotta always verify after you run your models in Darwin Designer, right? Because maybe the diameter and the sizing is fine, but now you got another problem, which you're gonna have anyway, which is the pump curve, the capacity of your pump isn't enough to handle all of those flows. Okay, so here we can get a better sense of what the pressure would be like for all our scenarios, right? So we can then compare and see, oh yeah, this really is a better scenario. And you can do the same for the solution 1, which was this, the trade-off, and the solution 6, where we had those diameters. Remember, this one would be 12 and these would be 10. So let's see if we can just use, because our demands didn't change. Okay, so our demands are good now. So let's run those two and we can compare apples to apples. Let's run them all. Okay, so you notice our demands didn't change because they're the same in all of them. But now I'm going to do a data table and I'm going to compare the pressure when I'm doing minimum cost or when I do the trade-off solutions 1 or 6. Okay. So there we see it. Minimum cost gives us 24.9 psi. A little bit more money. I think this one was 206,000. Better pressure. But if we had more money, we can go up to 35 psi at that node. Okay. And we can go back to the Darwin and see how much actually it was. This solution 6. Solution 6 was 252. So not that great of a cost, just a marginal 50,000 or less than 50,000 improvement over this one, yet your pressure goes from 25 to 35. Okay, why do we need to export the information? Because Darwin is just crunching numbers, but it's in this sphere of Darwin Designer. Nothing that you do here automatically transpires to a scenario, right? So you can do all the runs that you want, you can do 100 solutions and change one thing, change the other without having to create 100 scenarios, right? So when you find one solution that you like, you then export it and then you see, okay, under these operating conditions, what's my pump going to be? What's the pump operation point going to be? Do I need to turn on another pump like you probably would in this case when your demands get to be so high? Most utilities would have kind of a jockey pump that only turns on when your demands go really high, like in this case of the fire. So all those detailed hydraulics of the entire system you get to play with after you export the results as a scenario. And what gets exported here, which is important to remember, is the physical alternative, basically telling you pipe diameters, and active topology, basically telling you which of the pipes that were optional are not going to be part of this one alternative. Okay?
If you found this video helpful, please give it a like. If you want to see more such series, consider subscribing to our channel. Thank you, and see you next time.